You know, when I was working at the Mathematical Institute, it was always tricky to explain to people what I actually did. My family, my friends, I think the average person really doesn't have a clear idea of what mathematicians do day to day. Well, computer science is in very similar position. I remember a friend once asked me, "You study computer science? Does that mean you learn how to press the keys faster so you can type quicker in Word?" That kind of sums it up. People often don't understand what mathematics, computer science, or even physics really look like in practice. So today I want to give you a little peek behind the curtain. I don't think math is taught completely right in school, from elementary to university. What we learn there is very far from how math is actually used in real life. When you are a mathematician working at an institute, you don't sit all day solving sheets of equations. It's not like an exam, it's not even close to that. Let me give you an analogy. In driving school, at least in my country, Czechia, you have to pass both written and a practical test. In the written one, you get questions like, a blue car is coming to the intersection, a red car from the opposite side, and the yellow car from the right. Which one goes first, second, and third? It can get complicated, but when you are actually behind the wheel, you are not thinking like that. You are just deciding, should I go or should I stay? Well, still, what they teach you in driving school is important, even if you'll never consciously use it. It's the same with math. At school, you learn how to compute things, but in real life, that's not how math works. I was lucky to have a great math teacher in elementary school, Mrs. Hozova. She was very practical. We didn't do computations just for the sake of grades. She always explained things using real examples. For instance, she would say, a car starts from place A and wants to reach place B in a certain amount of time. What should be its average speed? You weren't given the equation, you had to build it yourself. That's already much closer to what mathematicians actually do. Back then, I didn't realize how valuable that approach was, to be honest. But now I see it clearly. She was teaching us how to think like mathematicians, not just how to compute. Math is not about computation. It's a language and a tool set. There are even discussions about whether math should be considered a separate science or just the language of science. But its purpose is clear. It helps us describe, predict, and explain reality. So I'm not interested in computing an integral's exact value. I might not even know how to do it anymore. And that's fine. What matters is building the right equation or model and understanding what that integral actually means. If I already need to compute something, I use tools. MATLAB, R, Python, Mathematica, Wolfram, even large language models nowadays up to a certain level. The computation itself isn't the important part. The important part is the model, the idea behind it. In my case, the piece of reality I studied was computer graphics. You might see an image as just a picture, but for me, it's a mathematical function, a function of x and y, where the value represents pixel brightness. 0 means black, 255 means white. Once you represent an image as numbers, you can do math on it. Let's say some pixels values are missing. You can estimate them using the surrounding ones. If the pixels to the left and right are both 5, it's unlikely the missing one is 250, minus 10. Probably it's around 4 or 5, because that's how real images look. This idea is to image in painting, a field I worked in before generative or AI took over. We can talk about it in a separate video. You take a damaged image, mark missing parts, and let the computer reconstruct them. That's practical math in action. We are not sitting and calculating numbers by hand. We are building models that describe reality and then using computers to compute the details. Let me give you another practical example. Imagine a factory that produces specific parts. Some of them might come out damaged. One way to deal with that is to pay someone to sit and visually check every single product and manually remove the defective ones. But there's a better way. You can set up a camera and build a computer vision system that automatically detects defects. That's a math in action again, but not that kind you do on paper. You capture the environment, turn it into numbers, and describe what a good product looks like. Its shape, color, geometry, even how light reflects off it. Then you build a mathematical model that distinguishes good from bad pieces. That's what practical mathematics look like. When I was a kid and we learned sets of equations in school, once I learned the algorithm, it got boring. So I wrote a program in Pascal to solve them for me. I would type the numbers, the program would print the steps, and I just copy them down. That's when I realized the fun part for me isn't solving the equations. It's building the system that solves them. And that's computer science. Building the equations, that's mathematics. That's the essence of applied math. You model reality, you formalize it, then you let the computer crunch the numbers. So why do we still teach computation in school if mathematicians don't really do it later? Well, they might do it later, just to be candid. But, well, we teach it because it's good mental training. It develops logical thinking. It's like solving puzzles. Not always practical, but great for your brain. Once you move beyond that, the real challenge is not solving equations, but creating them. That's what mathematicians do. We build theories and models to describe reality. Sometimes the models are even unsolvable in practice. They might take millions of years of computation. In those cases, we simplify, approximate, well, or change the model to make it workable. Math is beautiful because it's precise. Words can be ambiguous. Math can't. I can express a complex idea in one line of equations that would take paragraphs to describe in words. That's why we use it, not to impress or confuse crowds, but to be efficient and ambiguous. When I write papers full of formulas, it's not about the numbers, it's about clarity. The math just helps me say what I mean precisely. So what do mathematicians actually do? We don't sit and compute equations. We build models that describe the world. And we let the computers handle the computation. If you are a student, remember, math is not just about solving for x. It's a language that helps you understand the world around you and communicate ideas clearly. That's what makes it powerful and beautiful. So, that's all for today. Thanks for watching. If you like what you saw, don't forget to hit the subscribe button. See you next time.